Okay, hello. Good morning, everybody. Um, Glad as always, happy as always to have some of you join me. Good morning, Magenta. Nice to see you as always. We're in week 8. We're darn near halfway there. Good morning, Edcast. Nice to see you. Happy Monday. All right, so week 8. There's a few less people turning in labs this week, so hopefully that was just people we're taking a break that is kind of offered in the free drops of 2 assignments. But anyway, if anyone's struggling, I haven't really heard much from anybody in this class, so use the regular channels if you are finding places where you struggle. But the labs that were turned in, which was 90% of everybody, were great. So I'm glad that the work I can see is all going really well for you guys. All right. Anyway, so week 8, I have a lot to talk about today, so I'm gonna get rolling here pretty quick. So just where we're at in terms of the schedule. So we're coming up to the interesting stuff pretty soon. So this is the class is called Programming and Algorithms 2. A lot of the algorithms that we will deal in is to use and create data structures. Using data structures that other people created is a lot easier than creating data structures for ourselves. But the experience, which is what we'll do for the second half of the class, really, of creating your own data structures is a very good one to have. Then you'll understand kind of what the programmers who created things like vectors had to go through to create those structures for you to use. So we're in week 8. This is the really the last week where we will be using a lot of the ready-made data structures, and then pretty quick here we get into using other people's creating and using our own data structures. So individual project 2 is still out there a ways, but after today you have everything that you need to do the second project. So hopefully you'll take advantage of that in terms of your scheduling. So there is nothing more I have to offer to help you on the second project. There's nothing more that you need in terms of the second project after today, even though it's not due until October 30th, but that's just to kind of give you the full 4 weeks to work on it. Okay, so week 8. So here's what we're going to do this week. We're going to create a struct, which we've already done. We are going to create a class, which we've already done. But we're going to create a class whose job it is to manage a collection of that struct. So, and we're going to use a vector as the underlying data structure. So this is kind of a big moment in the semester where we have kind of all the big moving parts that the rest of the semester is about happening. So we have some kind of data we want to store. So we structure that data somehow. The most basic way to structure data is to create variables for that data. But then we often, if we recognize that we have multiple variables kind of associated with the same sort of conceptually piece of data in our program, then we'll often create a struct or a class. My personal sort of way of deciding is that if I just need a place for variables and not really much for functions, then I use a struct. If I need a place for variables and a set of functions to kind of work with those variables, then I use a class. So we have structured data, which we're going to use a struct for that this week. And then we have a class whose job it is to manage a collection of that structured data, many instances, in other words. So the class will use a data structure inside of it and then offer functions that allow us to do a variety of operations on that collection. You can kind of think of this whole arrangement as something like going to the grocery store. The structured data is the items in the grocery store. Each of them has a weight and a quantity and a price and a name associated with them. And then you have a shopping cart, which is a place where you can store a bunch of those. And then you have an interface, a an entity that manages the items going in and coming out, and that's you, the shopper, or the wrapper around your shopping cart, because the items just don't fly in there. You have to take them and put them in there, and if you change your mind, you have to take them out and put them back on the shelf. So the item is structured data. The shopping cart is the data structure that holds many of that kind of item. And then the shopper themselves is the interface between the items and the data structure that's being used to store them, if that helps. Doesn't look like that, of course, on the screen, but that's one of the ways that I use to think about this kind of problem. The other thing we're going to do is we're going to use built-in sorting. So the standard library has a sorting routine that works on data structures that can be iterated. We saw two of those last week. We saw strings, which can be iterated, and we saw vectors, which can be iterated. And any collection that can be iterated, you can use standard sorting routines on it. So we're going to explore that. We're not going to write our own sorting routine. We're going to use a built-in one. At some point in your career, if you are a computer science major, you'll probably have to implement your own sorting routines as well. But I also think it's very valuable to know your way around the C++ standard libraries. So that's one of the reasons why that's here. And then with that, everything toolkit wise that you need for the project is in place for you. So we have a few references to sorting via the standard library sort routine. How could it possibly do that? We'll find out today. And then we have a lab. Let me open it. So it's structured similarly to last week's lab. You have a unit test in lab8.cpp. You have headers in inventory.h, and then you have implementations in inventory.cpp, which in this case has actually been set up to kind of help you through the process. So this week I offered all of the function headers, and I also implemented one for you. Why did I do that? I guess I felt like you had plenty enough functions to deal with already. So yeah, so there's that. Okay, and then we will look at what do we mean by CRUD? It's a programmer term / computer science term. The letters stand for create, read, update, and delete. These are the four sort of key operations that you need to be able or want to be able to perform on any collection. Create means that we want to add elements to a collection. Read means that we want to read the information that's inside of it, either by retrieving individual items or getting metadata about our collection, like how many total items are in it, or if it's items with prices, what's the total price of all the items added together in the collection, that kind of stuff. Updating, of course, is going in and updating one or more of the individual elements in a collection. And then finally, delete, which is the ability to get items out of any collection, which, as you all know from last week's discussion, you can't do with arrays, kind of. Depends, but sometimes you can kind of simulate a deletion on an array, even though we know that the array slot remains. Good morning, Tony. Sorry, I hadn't seen your good morning there. I'd said good morning to everybody else, but I didn't see you come in with the good morning in chat. So good morning. Sorry I missed that. And then last, the reminder. So lab is always, discussion is always, the time to look at what Project 2 is about is now, today especially, because all of the tools that you need to do it, you have after today. And we have used all of the tools in various labs now, or after this week's lab. Okay, so I'm going to go fire up a REPL and start working on vector stuff. Week 8. Yeah, the first thing actually before I do that, well, I have my REPL ready. Before we do that, let's go look at c++.com and let's look at sort. So standard sort, and I hope that it fits on the screen. Okay, I can. So these are hard to read. Or at least they're a little bit intimidating when you look at the top of the standard sort page. I'm making sure you can see it. It's not the best. I can blow it up a little bit. Get rid of the stupid ads. Okay, yeah, so it all fits here. So they're scary looking at first. The key part is to note that sort, at least one key part, sort doesn't have a return value. And what that will tell us once you gain some experience at this is that a sorting function that doesn't return anything must have to sort the element in place. So that's important to note. I'm going to pass it something and it's going to sort it in place, meaning it's not going to return a new one. It's going to sort the current one. So any sort that I perform on a collection is alters the original collection by sorting it, which is something to keep in mind if you want to keep a copy of the original kind of unsorted version. We don't need that, but something to keep in mind. This iterator first and last, I'm about to use this. So I'll show you how this works for vectors. It'll be the same for strings, and it'll also be the same for most of the collections in the C++ standard libraries. So when we do a sort, we are going to pass an iterator to the first element and pass an iterator to the last element of the collection to get the sort. Let me go grab standard vector and see where those functions are. So we need something for first, something for last. Okay, so this iterator section now comes into play. So unfortunately, the terminology is a little bit different, but this iterator begin returns an iterator to the beginning. That's the first element. So this is how we get to the first thing in a vector. And then end is the last thing. So begin and end on a vector are going to pair up with first and last on the sort, just to keep in mind. So let me add a vector in here. Let me use the space saving but lazy persons using namespace. All right, so let's make ourselves a vector. We'll just start with integers. And let's load it up with just some random stuff. Doesn't really matter. So an unsorted collection, right? And I will iterate it. In fact, let's make a function to print it to keep it clean. I can use a for each because this is an iteratable collection. All right, so everybody on one line, but that'll keep main a little bit cleaner if I do it that way. So let's print numbers first. And then we'll apply the sort and print it. So sort is in the algorithm header, which I note on the sort page. So I need to include algorithm. I keep my includes alphabetized. That's just the way I like to do it. And probably that's pretty typical for programmers. So algorithm, and that way I have access to sort. Although let's not be lazy about this, shall we? So I'm using the standard library sort routine. I wanted you to be able to see that. Let's go side by side. No, let's not go. I changed my mind. Okay, so this is just a quick print it out because I want to be able to print it out in its unsorted state, and then I want to sort it. So this is the standard sorting routine, and what I'm told is that I give it an iterator to first, which is the begin function in vector, and an iterator to last, which is the end function in vector. So I give it my vector, which is called numbers, at the beginning. It's a function, and my vector, which is numbers, all the way to the end. The interesting thing about these iterators is that you can actually, you can cause the sort to only sort part of the vector if you want. And you can actually do things like this. You can say, well, leave the first element, move over one from the beginning. You can actually do that. I'm not going to do it. I'm going to sort the whole thing. So to sort the whole thing, numbers from beginning to end, and then I'll print it again. And we can see that it did, in fact, sort. It took my original vector and sorted it in increasing order, which is just the built-in behavior. I didn't do anything to say how to sort. It just sorted. Let's try it with strings. Let's change this. We're about to get a technique to make this a lot less painful for ourselves as well. I'm just not going to show it to you yet because you might be miserable. So we'll print string vector. Did I using standard string? I did not. So I'm going to pause for a minute. So here's all my includes up to now. I included algorithm for the sort, IOStream for cout and inline. Some people will do this, by the way. They'll kind of comment what they're using just as an extra piece of reference. Just to make it easier to find things. So that's why I'm using algorithm is for sort. Why I'm using IOStream is for cout and inline. Why I'm using string is for standard string, and why I'm using vector is for standard vector. Because these things, these using directives by themselves don't tell me where things came from. So that's why I added that. That's also for you. All right, so here's a print function. Where I'm printing my int vector. I'm going to do the same thing for my string vector. I'll still call it v in here because who cares? These will be strings. Nope. No inline in the loop. I just want them all on one line. Okay, so there's my two print functions, and that's just to keep main a little bit less crowded as we get going. And then in main, I have where I'm experimenting with the vector of integers. Let's experiment with a vector of strings. I'll call them fruits, oranges, bananas, apples, cherries, one more. Kiwis. I wanted a short one. All right, so we will print string vector fruits. Then we will sort from the beginning of fruits to the end of fruits. So remember this beginning and end functions, these are built in to the vector. The vector, this is saying start at the beginning of the vector and go through to the end of the vector, which I looked at the documentation for that. But the sort routine needs that. It needs to know what and where to begin and what and where to end. So that's why that's there. And then I'll print it one more time. to see what it does with strings. Oh, I forgot to type a V up here. Oops. Okay, so more or less alphabetical order. That's not the fancy term for that, but we'll call it alphabetical order. So sorting seems to work, and it sorts ascending or increasing. And it seems to work just fine for integers and strings, and I can tell you it will also work for floats and doubles. Probably it works for bools, although I assume it just kind of clumps up all the falses at one end and all the trues at the other end. I'm not sure how useful that is. Anyway, so there's the built-in sort. We could go read about the algorithms that the built-in sort uses. Possibly. This documentation does not say what algorithm is used. There are different ways to perform sorts. Okay, so anyway, ints worked, strings worked. Now let's ramp up the complexity a little bit. In fact, I'm going to comment all this junk out and start with this clean screen. So let's make a struct. And first, let's populate a vector with struct instances and then go from there. So I will call it, I had an idea earlier. Well, let's just stick with the fruit theme. So we'll give each fruit string. I don't, no, I'm uninspired by that. Call it a car. I don't know much about cars, so I'm going to be making stuff up here. Make, model, a year. Miles per gallon, let's say. I'll spell it out so it is clear what it is. All right, so there's my struct. Let's make some and put them in a vector. So I will have a car, C1, and I will initialize it in this sort of direct way. When you're initializing a struct like this, you need to make sure that everything is in order. So the first thing, so left to right matches top to bottom. So the first thing is the make. You Ford Model T, 1920-ish. Let's say at 25. Miles per gallon was probably just horrendous, probably like 3.5 or something. So there's a car C2. Chevy, Mustang. I think they were making them by the late, and I bet those were also pretty miserable for fuel mileage. Ford, Chevy. Toyota, Camry. Let's make that a pretty modern one. And my guess is it's pretty decent. Something like that. All right, so there's 3 instances of my struct. Let's populate a vector with them. So I will make a vector of car. Call it cars. And then I will build it with these 3 things. And then I will print it. So let's make a print car vector. Just call it B. So this is a composition problem from the other direction. So I'm going to go ahead and solve these problems as I'm building this example. So I could print out all of the details of the car right here, but I don't like that. I think what I'd rather do is C out C dot to string, and then I'll make it to string function to string takes a car and then an end line. So I am sort of decomposing this problem. I have a vector. If I loop through it, I'm going to get cars, but I'm going to go ahead and separate out the function that prints the details about the car into its own function, because that could come in handy later to have that separate. So you may find yourself over-engineering your software a little bit as you get comfortable with the approach that I'm using, meaning that you end up with 10 functions where 2 might have made sense. But go ahead and let yourself over-engineer software for a while, because that's really the only way, in my opinion, to develop your own feel for when should I decompose a problem and when should I not. So I am decomposing the print car vector problem by separating the looping of the vector from the printing of the details, which I'm going to make its own function for that. So string, this will be just a car, and then I'm going to need string stream. Wait, is that an output string stream? I think it's an iString stream, right? Okay. These I'm just banging out because you've seen these a whole bunch of times. So let's see. We need the make space the model. Ooh, we should put the year first. Maybe a comma? Stop there, and then I will put no new line. So, and I don't like to put new lines on functions like this, because sometimes a new line is not desired. So I'm not going to make that choice now. If I am using this function and I need a new line, I will add one, as I did right here. I'm also not formatting the miles per gallon because I don't want to spend time on that. But of course I could use the magic formula on it. I just don't feel like it because I want to save the screen space for it. Okay, so anyway, I decomposed the problem all the way down to the point where I have a toString function that I pass cars to, and then I get strings back. Okay, so let's print the car vector. Make sure everyone's happy. They are not happy. Oh, wait, what? Let's see where I messed up. Invalid operands to... Is it because it's supposed to be an output string stream? I bet it is. No one caught me on that. Okay, so there is my... okay, yeah, so Magenta thought maybe there's something wrong here. There was. I need to go out, not come in. Yeah. Oh, did I make it a Chevy Mustang? Oh, yeah, let's... There were 67 Corvettes. Yeah, good point. Ooh, I like Bel Air. I think it might be 1L. I could even go a little earlier in that case, right? Like 48 or something. Probably miserable gas mileage. Okay, so all of that is to get to the sorting thing. Well, it's no big deal, Tony, because I know nothing about cars. But Chevy could have made a Mustang. I guess if Lee Iacocca had worked there. But they didn't. Okay. So there's my little output. Now, why did I do all that work? Because now I want to do this. So this is going to take some reasoning because I'm about to get an error and it's going to take some work to understand what's going on. But in theory, if I have a vector, then I can sort the vector from the beginning to the end, just like any other vector. But let's see what the error looks like, which is a wall of error. So let's see if we can find where this all began. All right, here we go. So the evidence is hard to collect for this, but I also just want you to see what these kinds of errors look like. So this first one right here says error, invalid operands to binary expression car and car. And then it's referring to something that returns, basically is one car less than another car. And then I get a whole bunch more grouses about less than-y stuff. So there's another less than thing. See, yeah, there's an operator less than. Some weird stuff about template specializations, partial sort. Anyway, a whole bunch of errors. But the one that we are going to focus on is this one right here. So invalid operands to binary expression car and car. So what it's saying is somewhere in that sort algorithm was an effort was made to ask the question, is one car less than another car? And that didn't cause errors with the string and the int version, but it did cause errors with my car. So in some ways this is not hard to understand, and in other ways when you're looking at it in code it is hard to understand. So why won't this sort work on my cars vector? It's because at the end of the day, to sort a vector, C++ needs to know how to compare two items of those vectors, of that vector with each other. So to sort a vector of integers, C++ needed to be able to compare and see if one integer is less than another integer so that it could put the lower one first as it was sorting. So that worked with integers, and it turned out it worked with strings, because strings is programmed to do that. So when the sort function tried to compare to see if one string was less than another string for sorting purposes, it discovered that, oh, alphabetically you sort. That's how you know which comes first. So the problem with trying to sort cars is that I just invented cars, not in the real world, in software, right? C++ doesn't know what it means to say that one car is less than another car. We're going to have to tell it what it means that one car is less than another car because we just invented this type, this struct car. So we can sort a vector of cars if we tell C++ what that means. I'll show you in the documentation also where that appears. So here's the sort page. The elements are compared using either the operator less than for the first kind of sort or a comp function for the second kind of sort. This is the one that we want for our situation because I think it's easier for you to understand. So the second form of sort says, tell me where to start, tell me where to end, and give me a function that tells me how to compare things. So when you are using a vector to store a data type that you just invented, you have to create a function that tells C++ how these things ought to be compared with each other. So let's try it. So it says I need a function that compares cars. Fair enough. Actually, let's go read some more. Let's read this paragraph about what that function is supposed to be. So what is that comp function supposed to do? It's a function that accepts two elements, in our case, two cars, returns a value convertible to bool. Well, how about just return a bool? The value returned indicates whether the element passed as the first argument is considered to go before the second element, i.e. is less than the second element. So we need a function that compares cars, takes two cars, returns a bool, indicating whether or not by our programming C1 should come before C2. So what does that look like? Well, we have to choose. We can sort by any number of the fields in a car. We could sort by make, we could sort by model, we could sort by year, we could sort by miles per gallon, we could sort by a combination of make and model if we wanted to. But we have to provide a function that returns something that's truthy. We're just going to return true or false, that tells C++ whether or not it's true that C1 comes before C2. Let's do the most easiest thing. But the most easiest is easier than the easiest. Let's just return a comparison of the years. So if it's true that C1's year falls before C2's year, then we'll tell C++ that C1 should come before C2. That will just compare the years. Okay, so what does that look like in the sort call? We add a third argument for the second form, and we say which function we want to use, which is our compare cars function. It has to be a function that takes two of the things being compared, in this case cars, and it has to return true if our algorithm determines that the first element should come before the second. Now what that means is entirely up to us. We're going to say if the year comes first, then the car comes first. Let's try it out. So did it do it? So to see 25, 48, 20. Let us do instead by the make. So this time the Chevy comes before the Ford, comes before the Toyota. We could do something more elaborate. So we could say, well, no, let's not open that can of worms. If we want to, by the way, we can actually make multiple compare functions that capture these various ideas so that we can use them in different contexts, right? So we could sort by year as its own comparison function. Oh, good question, Edcast. So Edcast is asking in chat, where do these parameters actually appear? So in the sort function itself, you don't. You actually just say what function, and the sort routine actually calls the function passing the pairs of cars for you, which is pretty awesome, isn't it? So you never say which pair of cars. The sorting algorithm actually is passing in the pairs of the cars for itself. The fancy word for this, by the way, is a function pointer. So we're actually passing a function name as a parameter to another function, which then calls that function passing pairs of cars. Pretty neat. So let's see, compare cars by year, and then we will repeat the whole process and compare cars by make. Yeah, it's a very cool thing. Yeah, so Edcast in chat is saying it's pretty neat that it works that way. It is. It's super, super cool. It's hard to keep track of. I mean, you can't really see all these behaviors. Like I can't conveniently see anywhere where compare cars by year is being called somewhere in the code for the sort function, and that pairs of cars are being passed to it as part of the overall sorting algorithm. There's no convenient place to go look at the code that does that. So that part is unsettling to most of us, that I can't see it. I just have to kind of understand that's what it's going to do. So here's an example where I first sorted by the year and then printed it, and then I sorted by the make and printed it just to see if it was still working, which it did, which is pretty cool. So that actually officially is everything you need for the project. At that point, now that you know how to do the sorting relevant to the project. Oh, and by the way, you can trick the algorithm if you want to. So I could have ascending and descending variants simply by reversing the logic. So there's no rule that says that I have to go for an ascending sort. I can go for a descending sort if that is my desire, simply by saying, actually, I want to know when the second car should come first, and that's what I'm going to tell the sorting algorithm. So I can do sort by year, compare by year ascending, and then I can repeat that. And so that gives me a lot of control over that sorting behavior. It doesn't have to be ascending. I can actually make it descending at the level of the comparison if I want. So here's the ascending, here's the descending, and then here's the by make sort. So I have complete control, and I can use, I can write any logic in these comparisons that I want. So I can compare multiple fields, make and model, make model and year if I wanted, make model year and miles per gallon. I have complete control over that sorting. And all I have to do to alter the behavior is just switch the cars around and say that I want the second car to come first if its year comes first, which is effectively a sort descending comparison. So pretty neat, I think. Pretty neat stuff. I need the files view back. Okay, so there is kind of phase one. So we made a struct, we populated a vector with it, we did some simple printing routines, and then we looked at the way that you make a sort do a sort. So I'm going to move those around. So now let's do something bigger, which is now make our shopping basket come into play. So I am going to, I'll share the link to this REPL. I'm probably going to have 2 links to REPLs in the notes this week. So I'll share that one, and then I'm going to make another one for the second part. So week 7 CRUD, I'll call it. So now let's take that knowledge, so we can make a struct, we can populate a vector with it. We can sort the vector by implementing functions to compare elements of the struct. So now let's do something a little bit bigger, which is now let's do the whole wrapper class idea. So the wrapper class, the fancy word to use for that is an interface. But remember my example where we have items of food in the grocery store. We have the shopping basket, which is the data structure where the food items go. And then we have the interface between the items and the shopping basket, which is the person themselves. We create entries in the shopping basket by placing them in there. We read entries in the shopping basket by picking them up and saying, what was the price again of that? We can update those items sometimes. Well, we shouldn't on the price, but we could grab more oranges as an example and add them to our basket as an update. And we can also delete items from our basket by pulling them out and placing them back on the shelf. So we're going to do something similar, but in software. And I'm going to use all the same language that I just did when I create this code. So I'm going to call this shopper.h. And I'm going to put all of my headers into shopper.h. Pragma once. We do pragma once in the .h files only. And the reason we do this is because we're going to end up with software projects where we have to include a .h file. In fact, you're going to see it here in a moment. In fact, let's take it out. No, let's leave it, and then I'll take it out temporarily and show you the potential problem with it. Anyway, the top of our .h file, we put a pragma once, and that is to prevent the compiler from trying to process these headers more than once. And I'll explain to you when that can happen here in a moment. So only in the .h file do we do a pragma once statement. Now we're going to put all our headers, which is going to include our struct that represents food items. So we'll have a name of it. We'll have a category for it. I need strings for this. A name, a category. Well, if it's going to go in a... let's just go for a price right now and leave it at that. So there's our food item. A struct is kind of its own header and its own sort of functional thing, right? If you remember that by default, all the members of a struct are public. This is a case where I would use a struct because a food item is not really algorithms. It's just data. So I would typically use a struct here anyway. Probably, let's give ourselves... let's give ourselves, oh wait, no, that's not where that goes. Just the header. So a function that we can turn an item into a string for printing, should that come in handy somewhere. Let's do some let's set up for some item comparisons while we're here. So compare by name, 2 items. FI1, FI2. I'm going to group these together. I don't think I need... so let's do compare by name, compare by category, compare by price, All right, so there's my little setup just for the item struct part. That is my model, how I'm going to model the food item in the grocery store in software. The struct to capture the data. It's a string function, so I can print it on the screen when I want to do that. And then a few comparison routines so that when I start building a collection of these items, I can sort them in a variety of ways. Okay, so step 1. In fact, we will say so the word we would use for this is a model. It's the way that we are modeling a real-world object in software. I'll say standard. Actually, say it like that. So now we're going to write a class And the reason why we're writing a class instead of a struct here is because this class is a lot more about the functions in it than it is about the data, or at least the functions I want to create around the collection are an important aspect of what's about to happen. So I would create a class for this because there's a lot of functions that I want to associate with the thing. I create a struct. I could have used a class here if I wanted to, except for the comparisons are kind of weird if I had used a class. So to me, a struct made more sense for the data part of my system. The collection part of my system, I'm going to use a class. So what does it mean to create a wrapper around a vector of food items? Fundamentally, what it means is that. So fundamentally, what I mean when I say a wrapper around a vector of food items is a class that has as its primary data element a vector of food items. It's going to call it cart. And then it's going to contain functions that allow me to perform the various operations on the cart that I would want to perform. And the idea of the shopper class is that my functions will be easier to read and understand by their naming than the underlying vector functions might be. You'll see what I mean in just a moment. So I would call this a wrapper. You could also, if you wanted to, call it an interface. A set of functions kind of wrapped around the vector's operations. I'm going to need vector for that. I'm also pretty sure I'm going to need string stream, so I'm going to go ahead and include that and using it. So the .h file should have all of your library includes and using directives in it because they are part of what the .h file is documenting. So other programmers in theory should be able to open only your .h file and see everything they need to see about what's going on here. The actual code that has the algorithms in it, that should not be something that other people need to read unless you've made a mistake. So I put my includes and my using directives in my .h file because some other programmers may come along at some point and they don't want to be bothered with the actual details of my code. They just want to see, like, what are the functions and what are the classes and structs going on here, and that's it. What are the library dependencies? Okay, so I know that this thing is coming though because of this toString right here, and probably I'm going to have a toString here as well. Okay, so what kinds of functions do we have in a wrapper class like shopper? And remember, its job is to wrap kind of nicer sounding functions around less nice sounding vector functions. And I sort of just as a default, whenever I'm creating a class that I'm using to kind of help me clean up the way that I access a data structure like this, I always do the CRUD operations plus a toString function, at least for testing purposes. So hopefully this will begin to make sense right now. So the C part. Means to create an entry, which we would often say add an item to a collection. But if I said add, then we'd have arud, and that wouldn't read as cool as CRUD, right? So one of the reasons why the CRUD, what's the word? Not initialism, acronym. One reason why the CRUD acronym is there, I think, is because it sounds kind of funny and cool. So the C part of CRUD means to create an entry. What does that look like for a shopper, which means really to add a new item to the cart? Well, it means this. So it will be easier for me to write my shopping application, I would argue, if I can just sort of think shopper.addItem item. So one of the reasons why we write these wrapper classes is because we can use function names that match the theme of our application. Hopefully that makes sense. So the theme of our application is going to be grocery shopping. So we have a food item struct to model the data, and we have a shopper class to manage the cart for us. So shopper.addItem food item, which sounds like the theme of the application that I'm developing, which is one of the big reasons to do this, at least in my opinion. So that's how we'll create an entry. We need to be able to read an entry, which really means get item. To get an item, so usually when you're reading an item from a collection, you need to know what about the item will you use to match and retrieve it. So I would say for now, let's just start with indexes. Or should we say by name? Yeah, let's say by name. So we will use a name. So we'll get an item by name. So that's what it means to read an entry, is to simply sort of grab a copy of it so that someone can see the information about it. That's the R part. The update part. So we would have a... what am I doing? That stuff goes on the next line down. So we'll pass in a food item that contains updated information about one of the present items and then use that to update the item. So that's the U part. So, but hopefully you kind of notice that the function names match my shopping theme, which is one of the reasons to write these wrappers. The other reason is to write additional logic as needed. And then the last one is delete an entry. And let's return true or false whether or not we can find and delete the thing. Delete item, and we will delete an item by its name. So there's the CRUD operations. Adding an item, getting an item, updating an item, deleting an item. Let's say remove an item. Maybe we should return... No, we'll just return true or false whether or not the item came out. And then finally, which is useful at least for testing purposes, doesn't require any parameters. Okay, so there is a wrapper class. Why we say wrapper is because it is wrapped around the operations of this vector here. And the wrapping is the functions I have created, which speak to my theme items: add item, get item, update item, remove item. So the functions are kind of written around my shopping theme, but inside of them will be where we actually use them to access the vector and do the vector specific things. Okay, so that's step one. I'm doing okay on time. So let's go to step two, which is to implement all these darn functions, which is the less fun part. So I'm going to copy all the struct function headers first. I'm going to make a new file, call it shopper.cpp. So we need to make sure that shopper.h is included here so that all of the definitions, the declarations are picked up. And then I will go ahead and prep these for implementing them. And you'll notice here, so these functions are just functions coming straight over from the .h file. They're not embedded inside of a class or inside of a struct or inside of a namespace. They are just functions. This is just like last week's lab. Let's go ahead and do them real quick. So let's see, output. We have name, category. So I'll do i.name. And then I will, I just like square brackets. Category. Actually, that should come last, I think. Let's put a i.price, so I'm going to need a space and a dollar sign. And then i.price, which is going to need a little bit of cleanup. This line of code's getting a little long, so I'm going to push it down and kind of line it up pretty below. I should do, except for I don't remember the magic formula off the top of my head, so I have to go look it up. All right, compare. So return fi1.name is less than fi2.name. fi1 dot, this is category, less than fi2 dot category. So these are all ascending order compares. So there, that's the end of the struct part, and I'm going to move down and now get the class part. So that's these things that are all from inside the class. So I have to be careful about that. Let me shift tab these over. So because these came from inside the class, these are going to have to be resolved back into the class. So I do this part first. You've done this as well. It's just bringing multiple parts together in one lab. And then I'll prepare to implement them. So notice that I can, in fact, implement both my struct, sort of just my out in the open, not connected to anything in particular functions. They're not inside of a class. They're not inside of a struct. They're not inside of a namespace. So I can implement those here from the shopper.h header. And I can also implement the shopper functions from the class shopper that's in that same .h file. No problem. Okay, so when I'm adding an item, what that really means is I'm going to go to my cart and I'm going to push that item back into it. That's it. So that's not super exciting to write a wrapper function for adding an item. I guess one thing we could do, in fact, let's do it. Let's make sure that we don't already have an item by this name. So for food item in this cart. So here's where I'm actually using the wrapper to get extra logic in the program. So I'm not just going to add any old item. I'm actually going to take advantage of my wrapper function to make sure that I don't. So if oops. I have fi up here, fi here. I'll call this one item. I already have it. And there's no sense looking anymore. So I'm actually going to take advantage of my wrapper function to prevent duplicates from coming in. So when I am asked to add an item, the first thing I'm going to do is look and see if I already have it. I'll assume that I don't. That's what this is saying. Let's assume that it's false that I already have it, i.e. I don't have it. And then I'm going to loop through the items that I do have in my carts. And if I find an item in my cart that matches the item we're trying to add, then oops, I already have that. The search is over The break will break the nearest loop, not the if. Now down here I can say if I don't already have the item, then it is safe to add it. There you go. I could make this even fancier, couldn't I? Let's leave it at that. Okay, so there's a good wrapper function that is actually putting things in the cart, but only if it can't find them already being here. All right, reading. So what does that look like? So we'll make ourselves a food item. We will loop through our cart. And if the name I'm searching for is matching the name of one of the items in my cart, then that's the one I want to keep. I'm done looking. And I'll return that found item. That's how that'll work. Updating an item. So same kind of problem here. So I will say, I'll loop, so for food item in my cart. I'm not saying, yeah. So for in my cart, if the updater, that's the parameter's name, is equal to an item in my cart, then let's update it. And I'm going to do it manually. So the names must match, but perhaps they are, oops, we need this to be mutable. So we'll update the category, and we'll update the price. And that should be the end. So it's a lot. I'm going kind of fast. I'm going to provide you with a link to all this. But anyway, hopefully, as I'm at least walking you through the thought process. So what does update item do? Well, it receives an item that it's supposed to go looking for an item of that same name already in the cart. If it finds one, then it updates the category and the price of that item. Notice, by the way, that my loop is looping by reference. And the reason for that is because of the need to do in-place updates. This is not unusual, by the way, for an update and entry. It's going to have to actually either overwrite something or update something in place. All right, this one is a much bigger pain in our rear. So this one we need a vector algorithm for. So I'm going to go show you the function for it, and then I'll write the code to do it. So this is the vector page. And we need this erase function, which allows us to erase an element. So, oh, it's this one we want. We want the first one. So if we can locate an iterator on the correct position, then we can erase that thing. There's two ways to do this. I'll do them both so you can see them. Because this iterator is one of the weird things. It's that begin thing. So I'm going to do the erase in two different ways, and then I'll comment one of them out. So you can see what that looks like. So how do I remove an item by the name? I can't just use the handy dandy for each loop in this case, because it's not the item I need to affect, it's the vector I need to affect. I actually have to pull something out of the vector. So that makes this problem harder. So here's one way to do it. So I'll kind of use a traditional int I equals 0, although I'm using a size ti, which is good for counting through collections. Size t is just an unsigned integer, meaning that it can't be a negative integer. All right, I'll loop through the entire cart, and then I will use array style notation here. So if the name I'm looking for matches that's a lot to get at the individual field. So I have to go to the cart. I need to use the array indexing style, which I could also write as this. Up to you which one you think looks better or worse. I'll put them both here. But this one's different because I'm not fiddling around with the individual items. I'm actually fiddling around with the vector itself because I got to get an item out of it. All right, so if the name I've been given matches the name of an item in the cart, then I need to get this thing out of here. So one way to do it is this cart.erase. So you have to use this iterator thing to get to the beginning, and then you offset from there to the I element that you're trying to get rid of. And at that point I'm done because there should not be any duplicate names in there anyway. So here's one way to do it, which is the code is probably the scariest thing we've seen in code so far. So this will take some study. To unravel these things. So what is this cart? That is the cart that this shopper is wrapping. What does the index I mean? That means one of the items that's in the cart. What does .name mean? That is the name field of one of the items that is in the cart of this shopper. That's what all that means. So this next line, what does this mean? Well, I want to take this cart, this shopper's cart, and want to erase an item. What item? And unfortunately, this is the only way. These are the only ways to do it. So the item I want to erase is not at the beginning, but this many items over from the beginning. And unfortunately, you have to start at the beginning in one way or another for this to work. I don't even know if this is going to compile. Oh yeah, it's not called item, it's called food item. That is somewhere I called something an item, food item. That probably came from here. Food item. You'll have access to all this in its state because I'll give you the link. Will that compile? I knew I'd done that somewhere. Pluralized carts. There aren't many carts. There's a cart for a shopper. Except for if you've ever worked at a grocery store, which I did when I was younger. Except for people who come in 5 minutes before you close and then fill 2 carts. But this is a more ideal shopper who doesn't do that to the people working at the grocery store. Okay, so everybody prints. Compiles. So we were working on remove item. So this is the less scary one, as it turns out. I'm going to do the more scary one here. Or maybe I shouldn't. Maybe this is enough. Yeah, let's not open that other can of worms. Let's just do it this way. There is one other way to get this iterator going, but I'm not going to do that just yet. Too much. Okay, so there is how to remove an item. It's not a lot of code. It's just hard code to read. To string. So let's do the same thing here. String output and output. And then we will. So what I like to do for testing purposes, at least, so items in cart. And then I can use the size of the cart for that. In this case, I am going to put new line characters. Let's not do 2. Let's just do, yeah, let's do 2. It'll look pretty. 4. food item in this cart. And now I will thank myself because the food item, I already wrote a function for that, so thank goodness for that. Yeah, so there we go. There's the toString routine. And I have been going fast today, but I'm leaving the code in this complete form out there for you to study. And then hopefully if you need, you can watch and reverse my descriptions of what I've been doing on the video. So I've done a lot today. This is really the most new stuff, is all this sort of craziness with the vectors themselves, which takes some getting used to. Yeah, so let's go set up our main and test it out just a little bit. So notice that there's an include shopper.h here, and that's the way I tie the CPP file with the .h file together. But I'm also going to add a shopper.h here. And because shopper.h is included twice, it's possible that the compiler will, when it sees this include, it's going to go to shopper.h and try to read it. And then it sees the other include for shopper.h, and it goes back to shopper.h and tries to read it. And if it reads the same headings twice, you get an error. So the way we dealt with that problem is we told the compiler, don't come here if you've already been here. So if you've already been here once, don't come a second time. That way, even though we have to have the two includes, that doesn't break anything. For having the two includes, the .h file, even though it's included twice, will only be read once. Also makes the compiler go faster. Okay, so how do we test this out? Well, let's make a food item, test it out first. So they had a name, orange, which is in the fruit category, and I have no idea how much those cost right now. And then so we're going to test out the food item by itself first. Which didn't work. Oh, shoot. What? What in the heck are you talking about? ENDL. I did mean standard ENDL. Why won't it read it? That's weird. How interesting. I have no idea what that is about, but I'm just going to nip it in the bud. That end line. What? That is... Oh, shoot. That's not even here, people. Well, why am I undoing that? Just put it back. That is in shopper.cpp, line 85. You know what? Instead of, I'm just gonna put a new line character instead. That way I don't have to mess with any includes. Shopper.h line 85. All right, does that run? Okay, there's my piece of fruit. Shows its category. So the individual item works. Now let's make a few more. Put a couple in of that category. I have also no idea. I'm sure that's too low. I don't know. It's what came to mind first, unfortunately. And I also have no idea how much that costs. Okay, so now what we're going to do is test out our shopper. So I will put myself in the program. I'm the shopper. Let's see what I look like before I have created any items at all. Should be 0 items. So there is me. There are 0 items in my cart. Let me put a little separator up here. And put 2 new lines at the end of it. Why I'm going inline happy, I don't know. Okay, anyway, I just want that little separator there so that we know it's the other section. Okay, so before I've put any items in the cart, it's 0. That's correct. So now let's do some tests using our wrapper. So I don't have to think about the vector anymore. Whatever code there is handling the vector is no longer my issue. All I have to say is void.add item, and I will add fi1. That's it. And then I will see if the item got in there. So there it is. 1 item in the cart. There it is. Let's add the others. So I know we're getting a lot of moving parts here, which is part of the training, of course, is to be able to kind of in your head keep these separate interests in mind. I just wrote the code for it, so I'm familiar with what Shopper does. It's an interface to manage my vector for me, which gives me kind of Shopper themed function names. And I remember what food item is, because I just created that as well, but really it's just the data about an item of food that might go in my cart. The vector itself, I don't notice I'm doing nothing with the vector here because all of that has been handled by my wrapper class. So there's the 3 items. Looks all right. Oh, we didn't add the ability. So let's add the ability to sort. So let's go to shopper.h and let's add to the shopper class a sorting routine. Sort by name. And that's all the function really has to say from here. Sort by name, and then I will go to CPP, and I put that right in here, I believe. Shopper, sort by name. And then I will do, I need the algorithm. I need algorithm now. So back to the .h file, I need algorithm. And I need using standard sort. So that's the .h file. I updated my dependencies. The .cpp file, I can now say sort this cart.begin all the way to this cart.end. And then I will use compare. What were the compare functions called? Compare by name to compare the individual items in there. Where did that go? Here it is. Compare by name. Semicolon. Okay, so that's my updated shopper. So now back in main, I can say void.sort by name, and all that magic happens. And then I will print it out again. I know I'm not happy with the extra line between items in cart and the first item. So I'm going to take one of those out. So I'm altering the shopper to string function to get that extra line break out because I don't want it there. Okay, that's a lot easier to see for testing purposes. So there's the empty one. There's after I added one. There's after I added two more. Same cart, but now they are sorted by their names. It's like magic, these wrappers. Right? So Boyd.sort by name, what happens? Well, multiple layers of things. And then to string, so that was all okay. Let's try an update and a remove and see how that works. So let's do a update item, and I'm just going to blast one in just like this. I think I can do it this way. So let's make the we'll update asparagus. I'm going to move it to the category gross, which it is, and I'll go ahead and leave the price the same. Let's see if it'll let me do that. It may not. Okay, it did. I can just dump the data in there. So we'll update asparagus, and then let's get the apple out. Oh no, it's just by name, right? So I give it a name and then it removes things. So I'm going to try updating asparagus, should be the category gross, which it is. And then I'll try to remove the item. The removals happen by name. The updates happen by whole items. So it's going to compare the name, but then it's going to update the category and the price. Why not make it more expensive? So let's see what we get. So asparagus is now in the gross category, and it is more expensive, and the apple got removed. And then, of course, the read, but I'm not going to implement that. So that's a lot of stuff that I just did. I'm going to go look at the lab real quick, and I think that kind of everything that I just did is this extended example will be the same kinds of things that you encounter on the lab. So I will also share this repository with you on the lecture page. Okay, yeah, so I've got like 2 minutes, so let's go look at. So I know there's a lot of moving parts there. And kind of dropping you in the middle of a bunch of moving parts. I don't know if that's easier or better for you, but my hope is that giving you these kind of labs that are already very much set up for you to kind of go into and implement pieces will be helpful. So let's look at lab8.cpp. So that's just unit test. You don't have to touch anything in there at all. Inventory.h. This is headers. It does need your documentation in it, because remember, a header kind of is documentation for the whole thing. The .cpp file is just implementation. The .h file is the documentation for all of it. So, which includes your information. It includes all the dependencies. It includes the declarations of things. So notice how similar this is to what I just did. Here are some compare functions, a toString function, an inventory class, which is a wrapper class. And if we go down, we'll see in the private section, there is a vector of item in there. I made actually item to string. Yeah, I made this one. I did part of this for you, but not all of this for you. Sorts, we did an example of that. Clear, heads up about clear is that you need to refer to the standard vector documentation to figure out how to do that. And the hint is that it is very easy to do that because vectors already know how to do that if you call the right function on them. Get item count is a wrapper function around the vector size. That's it. We just did something like has item. But this is just a return true if the item by name is in there, false otherwise. We just did something akin to update item, although this one's broken out by the separate fields. We just did a remove item. We didn't have a true false on our add item, but anyway, we've done variations on all of these things. And then this is just a slightly different arrangement of information to get you the practice on it. And at that, you will have everything that's needed for the second project, which is not due until October 30, but at the end of this lab, you've got all the tools. Okay, and then the CPP file, which is, I've already set up all the functions. I've implemented one of them, which is the item to string part. Anyway, they're all set up and ready to be filled in by stuff. As you hopefully note, if you were watching if you're at the end of the lecture or that you're here for the live stream, a lot of these functions are tiny things. A lot of them are tiny things. Some of them require some logic, and I have offered you samples of that in the shopper example we did. Okay, my voice is tired. Thanks for being so patient as I talked and worked quickly through that extended example, but I wanted you to see everything spun up from bare screen and then be able to explain to you why I was doing what I was doing. Thank you, Tony. I hope you have a good week as well. So thanks to you guys who could be here for the live stream. That's always appreciated. I like the questions. I like the interaction. It just keeps me going. So have a great week. Or I hope you're having a good week if you're watching this by video later. Piazza, Canvas Inbox, office hours as always. If you run into any bumps along the way, then use one or more of those channels to communicate with me and your classmates, and we will help you. That's it. So take care. Thank you, Edcast. Appreciate it. You have a good week as well. Also, Robo Genko, thank you. Have a great week.